Welcome to our review for sections 5.2 through 5.6 AP Calculus. This will be done in installments. I'm going to get through a few problems and have to stop, but we'll keep you informed on that. So the beginning of this, we have some related rates, some real common related rate type problems that we should be getting comfortable with at this point. A 10-foot ladder leans against a vertical wall. The one thing to note right now is that 10, that hypotenuse length ladder, that is constant. So if we take a derivative, that thing's Pythagorean, for instance, that thing's going away. That's going to become 0 at some point. And the bottom of the ladder is pulled away from the wall at a rate of 2 feet per second. I'm going to call this x. So this is dx dt. At what rate is the top of the ladder falling? Y, so we're looking for dy dt. We expect it to be a negative number if we keep track of all of our signs. At what rate is the top of the ladder falling when the top of the ladder is 5 feet above ground? So at some point we're going to have our y value equal 5. So this is clearly a Pythagorean. X squared plus y squared equals 100. At what rate is the top of the ladder falling? I want dy dt. Therefore, I'd like an equation with y in it. I've got it. Ideally, maybe I'd like it solved for y if that's convenient, and it certainly isn't bad. Do you have to do that? Nope, don't have to do that. Maybe it's easier not to in some cases, but I'm going to go ahead and solve for y. So I get y is square root of 100 minus x squared. So when I take the derivative of this, let's just forecast and see if it's worth doing. I'm going to get dy dt. That's wonderful. X is going to, some form of x is going to survive this derivative process, but I'm also going to get a dx dt. Well, when the ladder's 5 feet above the ground, I'll know what y is. If I know what y is, I can find out what x is. So I think we're going to be in good shape here. So let's go. Dy dt is, we ought to be good at this by now, 1/2 times 100 minus x squared to the negative 1/2 times negative 2x dx dt, chain rule. So we end up with the 2 and the 2 cancel. I get negative 1x, so negative x dx dt on square root of 100 minus x squared. That is dy dt. So I know dx dt is 2, and when y is 5, right here, that's when we're interested in, when the top ladder is 5 feet above. That makes this a 5 to 10. That makes this a 30, 60, 90. This is 5 root 3. So we get dy dt is negative 5 root 3 times dx2 over square root of 100 minus 5 root 3 squared. So where are we at here? We're going to jump up to here. I've got negative 10 root 3 all on square root of 100. 5 root 3 squared is 25 times 3 is 75. Or I get negative 10 root 3 on square root of 25 on 5, negative 2 root 3. So dy dx at that moment is negative 2 root 3. Let's answer the question. At what rate is the top of the ladder falling? So the top of the ladder is falling at a rate of 2 root 3, what are we working in, feet per second. Positive. Take into account falling. Okay, so there's our ladder problem. They're all going to be very, very similar to that on the ladder problems. Or if we have a maximized area type problem of a triangle in the first quadrant, we get a lot of little Pythagorean opportunities. Okay, inverted right circular cone, whose depth is 10 and whose base is 5. So that's the cone's depth. That doesn't mean that's what the liquid is in there at that time, but we have a 10 inverted by 5, so we got a 10 height, a 5 here. I think it's a really good idea just to take that little cross section, and we have 5 for a radius, 10 for height. I call this R, I call this H. Unless I'm interested in the slant height, I'm not thinking about Pythagorean right now. I'm thinking about a ratio of R to H. Now understand, that doesn't mean R is 5 and H is 10. Where the water is, the water might be down here. But it does mean R and H are in ratio 5 to 10. Or R is to 5 as H is to 10. Therefore, we're going to either use R equals 1/2 H or H equals 2R. Your cone problems, they almost all include that element of it. Okay. Whose base has a 5 centimeter radius, is dripping liquid at a rate of 1 centimeter cubed per second. That means dV, that's volume. dV dt is -1 centimeter per second. It's dripping. Excuse me, got a little cold. How fast is the depth of the liquid changing? Well, they're asking for dH dt. And this is the whole key to how we get started. If they're asking for dH dt, we want an equation with H in it. And if they're talking about volume, we want volume with H in it. Well, what do we know about volume? Volume is 1/3 pi r squared H. Now, I could take derivative of this and get dV dt, and I'm going to get dH dt, and that's wonderful, but I'm going to get dr dt's in there as well. I could deal with that later, but I'd rather deal with it up front. What I'm not interested in right here are having terms of radius, but I have a substitution for radius. So volume is 1/3 pi in place of radius, 1/2 H squared times H. Haven't taken the derivative yet. Volume is, when I square 1/2, I get 1/4 times 1/3, 1/12. I have a pi that lives on H squared times H, H cubed. So there's volume in terms of height. And now I can go to dV dt. dV dt, the volume is 1/12 pi, the constant survives, times 3H squared dH dt, or I get dV dt. Actually, dV dt is -1. -1 is 3 times 1/12 pi on 4 times H squared dH dt. But we're interested when, how fast is the depth of the liquid changing when the depth is 5. So at H equals 5, I get -1 equals pi on 4 times 25 dH dt, or dH dt is, I'm going to multiply by 4. I'm going to divide by 25 pi. So dH dt is -4 on 25 pi. Let's answer the question. How fast is the depth of the liquid changing? Changing. So if I'm going to answer changing, then I'm going to answer with the negative. Perhaps we could say that the depth is falling at a rate of 4 on 25 pi centimeters per second. But if I'm going to answer the question the way it's asked, I'm going to say the height is changing at a rate of -4 on 25 pi centimeters per second. I think it's a really, really good idea to restate the question. Okay, let's continue on to the next page. Two cars are traveling away from the airport at straight path. Car A drives north. So here is car A driving north. If I call this distance A, the dt is 40 miles per hour. Car B heads east at 25. If I call this B, dB dt is changing at a rate of 25 miles per hour. How fast is the distance between them increasing when car A is 20? I'm going to call this R. So how fast is the distance increasing? I want dr dt. I want equation on R. So R squared is A squared plus B squared. I've got some information on A and B. I want to know how fast is the distance between them increasing when A is 20 and B is 7. So what happens if I take the derivative of this now? I'm going to get an R. I'm going to get, if I take the excuse me, derivative with respect to t, I'm going to get an R. I'm going to get a dr dt. Well, I want dr dt. I'm going to go ahead. I'm going to get an A. I'm going to get dA dt. Well, I know those. I've got A and I've got dA dt. I'm going to get a B, and I think it's worth taking the derivative. Now, you could take the square root, both sides. I'm going to go ahead and do it this way. 2R dr dt equals 2A dA dt plus 2B dB dt. And by not solving for R, maybe I did a little more upfront work, but maybe I don't have to deal with that square root. Who knows? Who knows what was better? So when A is 20 and R is 7, I want the square root. It depends whether we want exact answers or not, but I want the square root of 449. 21.1896. So I've got that answer loaded. So I'm just going to, let's see, that is 2 times, I'm going to go square root of 449 right now. dr dt equals 2 times A, that's 80. Oh, excuse me, 40, sorry. That's 40, 2 times A times dA dt times 40, plus 2 times B, 14, times 25. So the R dt equals 1600 plus 25, I don't know, I'm going to be lazy, 14 times 25, embarrassing, 350 plus 350 on 2 root 449, or 1950 on 2 root 449. If we'd like, that is approximately 1950. I'm going to go divided by square root 449. Oops, I got a 2 in front of there. About 46.013. So I'm increasing. How fast is the distance between them increasing? Well, it does kind of make some sense. The distance between them would be increasing based on A going, it's got to be bigger than, it's got to be increasing faster than A, which is 40, and faster than B, so it has to be increasing faster than those, so that seems at least reasonable. So, question, how fast is the distance? So, the distance between them is increasing at a rate, doesn't matter, whatever I do, I always need this little space, at a rate of 1950 on 2 times square root of 449 miles per hour. Okay, and then we hit number 4. And maybe we should put another category on it, because this is not a related rate problem. Let's read it. Starts out, we think it is. A cylindrical tin can is to hold 50 cubic centimeters of tomato juice. So we got a cylinder here. And the real logical question should probably be, if we're making this, hey, we want to send out 50 cubic centimeters of tomato juice, but I'd like to minimize my cost by using the least amount of surface as I can. So how should the can be constructed in order to minimize the amount of material needed in its construction? Well, here's our surface area. I want to minimize that. But what do I know about our surface area? Well, it also has to have a volume of, and volume of 50, volume is pi r squared h. So 50 is pi r squared h. Now, I've got, right now, big area equals 2 pi r h, that represents the lateral area, plus the top and bottom, the two circles, plus pi r squared. This is a function, this is a of r and h. I would rather it just be a of r, or a of h. So, since I only have one h here, I think I'm going to solve this equation for h. H is 50 on pi r squared, and I'm going to put that value in for h. So I get area just in terms of r is 2 times pi times r times 50 on pi r squared plus pi r squared. Alright, let's get a little simplifying here. A of r is, pi cancels, one of the r's cancel. I get 100 on r. Is that right? 100 and r cancels, pi cancels. I get 100 on r plus pi r squared. That's the area. I want to minimize area, which means I want to find the derivative, negative 100 on r squared, we've done that type of thing a lot, plus 2 pi r, and I want to set that equal to 0. Because the function, when its derivative equals 0, those are points where we might find maximums or minimums. Now we're just algebra away. So at this point, I'm going to multiply both sides by r squared. 2 pi r cubed, and I end up with r cubed equals, I would add 100, divide 2 pi, and I would get r is the third root of 50 on pi. Now, is that a maximum? Is that a minimum? We could do our little a prime test. Here's a prime of r. Somewhere in here, I don't know, 50 divided by 3, about 17, third root is 17, I don't know, somewhere between 2 and 3. We've got third root of root 50 on pi. And that's our only solution to this. So if I put in, so here's where the slope is 0, if I put in a bigger value, like say 10, if I put 10 in here, I get negative 1 plus a positive. The graph's going up. If I put something to the left of there, like say 1, I get negative 100, oh, it's negative. So it's going down, coming up, that's a minimum. So there is our minimum choice for our radius. How should the can be constructed? The can should be constructed with a radius of third root of 50 on pi, and then we can go back in and we can figure out what our height should be. Okay, I'm going to leave that to the reader, but I'm going to go into my calculator and confirm this value. So again, there's our radius. If we want to know our height, we can put that value right here and go through the algebra to figure out what the height should be. So let's go into on y equals, and you can see here I've got, is this my equation? Here I've got negative 100, is that negative? 100, should it be positive, should it be negative? I don't know why it became negative here. It should be negative. Now I'm nervous. Second insert, negative. Yell at me quick, maybe I'll hear you if that's wrong. 2 pi x squared, 2 pi x squared. Oh, no, I'm just going back to the original area formula. I'm just trying to maximize the area, I'm not trying to maximize the derivative. There we go. So delete this. Whew. All right, and I went ahead and set my window 0 to 20, and I zoom fit this guy. Go to my graph, and there we have our, that represents the height of that function represents the area. So I'm going to second calc minimum. Second calc minimum. And the bell's ringing. And just in time here, we're going to find that value.
Malia Miller, Barley Yetterberg.
I get approximately 1.9965.
Peyton
And
Trendman,
if I go back to my y equals, right up here, here's my, see if I can get back to that value. There we go right here, and there it is. So that is a solution I am comfortable with. So again, still got to do a little bit of discussion on this, talk about the radius, and talk about the height, answer the question. There will be more to follow with the remainder of the practice test. Thanks for watching.